Okay, now let's go. So, keeping, I mean, yesterday we did like the relationship between K and Young modulus. Today we will do area under the graph of stress versus strain. Okay, and this is something very, very important. So, let's suppose a graph is given to you. Stress in pascals and strain. The graph looks like this. So when you go to find the area under the graph, so I just want to tell you the area under the graph would be equal to half times stress times strain. Now, previously in this chapter, we have learned two things. We have basically learned that elastic potential energy is equal to half times force times display extension, right? And we also know that the volume is equal to the area times the length, really. So now if you look at this part again, you would actually realize that then the area basically gives you half. The stress can be written as F upon X, and the extension can be written X upon L, like that. Sorry, force over area. And now if I just multiply, if I write half times F times X and area times length, that would be it, right? If you notice something very, very cool, that on the top side we have elastic potential energy, and at the bottom we have volume, which basically means that, write it here, note, area under graph of stress versus strain gives us energy stored per unit volume, and that's something you guys need to remember, because only from the force and extension graph we can get the energy, but from this we only get energy per unit volume. All right, any questions, please let me know. Okay, Hamad, Javeria, do you guys understand? Aman, Aisha? Okay. Now, from this point onwards, we're going to then look at understanding the force and extension graph of rubber. Something very, very important actually. So basically, when you basically load the rubber, it shows you a very unusual sort of extension like this. So this is basically the loading. Loading means that you're putting weight on it, and then when you unload, it basically comes back like this. Not from the same point, okay? Now here, I'm going to show you three different things. So first, I'm going to show you the area under exactly loading. So I'm going to color this with this green, just so you can identify what is what. Then I'm going to color the area between loading and unloading with blue, and then I'm gonna color, what should I pick really? Okay, pink. So I'm gonna, pink would not go with this, let me think about it. Dark green, orange, purple. Okay, let's go with purple. Wait. So this area, which is under the whole unloading, okay, thingy, like this. So we're going to go with purple, right? So now we need to understand what these areas mean. Okay, so first of all, let's talk about the green area. So the green area is basically known as the total work done. Okay, in fact, any loading graph would give you this. And then the blue, the blue area gives you the energy dissipated in other forms. And then you have the purple one, which is underneath the unloading one. So we can write that this is the energy recovered, which means this was the energy that helped us unload it completely. Do you guys understand what I just said?
Sir, can you repeat?
Yeah. You see, green area is under loading. So when you're loading it, you're stretching it, so you're doing some work on it, right? So the total work, if you want to find the total work that you did, would be the one that is underneath loading. Do you understand this?
Yes.
In fact, what I'm going to do is, I'm going to erase all this. You might get confused then. Oh no. And that is a tough job to raise, but it's okay. Okay, so the green area I mean is this hole. Okay, Aisha?
Yes, sir.
Okay. I did not copy this, that's even worse. And And the blue area is I shut this one. You get my point? And the purple area is basically this one. Now you understand?
Yes, sir.
Okay. The energy dissipated in other forms being that, of course, if you keep on stretching the rubber, right, you'll notice that rubber gets really hot too. That's why. This is what it means, okay? Okay. Now, the next thing we're going to do is how to find the energy under a non-linear graph. And basically this is the same way we have done previously. I'm going to switch to the other screen just to draw, yeah, okay, this, and then I'll switch back. So even talking about the rubber one, so we've got to estimate it. We can't really do it directly because integration is not in our course. Alright, so suppose this is like 2, this is 4, this is 6, 8, 10, 12, 14, and this is 4, 8, 12, 16, and so on. This is force and extension, and this is meters. And now you have given like the loading curve, like this. And now they say, okay, find the area under the graph for work done. So what you're going to do is you're going to do the same thing. First of all, you're going to find the area of one box. So area of one box is like, you know, if you look at the box, it's 2 from this side, 4 from this side. That basically makes it 8 joules. And now you're going to find the number of full boxes. The number of full boxes are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? They are basically 12. And then just do number of half boxes. Half boxes basically are like the ones which are cut by the line. So I'm going to count them like 1, 2, 3, 4, 5. I'm going to count this, and well, I don't know if I should count. Yeah, okay, that's fine. 6, 7, and 8, and well, 8. So I'm gonna count this 8 and this one together because this is too small. Too small will come up. So this is just your understanding. So I'm going to do 8. And now what you should understand is that like 1 and 4 can combine. 3 and probably 8 can combine. 2 and 6 can combine to make one whole box, right? So it means if I combine two of them, it will make up one full box. That means these are actually 4 full. So, and then what I'm going to do is I'm going to just add the total number of boxes. So total number of full boxes, this is just estimating, would be 16 full. And then what I can do is I can say, okay, one box is represents 8 joules of energy, then 16 boxes would be how much, and I'm going to cross multiply this. So it's going to be 16 times 8, which is basically, let's find it through calculator, bad mental maths. So it's going to be 128 joules. Is it clear, everybody? Any questions? Let me know. Okay. Now, the last thing from this chapter that we're gonna do is basically, you can write this down. You don't need to draw this because I'm gonna put this, I'm gonna share this, okay, to you. So you can't really copy this, I know. So I'll share it to you, don't worry about it. For the other things, just let me know if you have a question, and we can go forward then. Okay. Now, so the last thing in this chapter that we're going to do is the loading and unloading graphs. And this is just to detect what is happening really. So there will be two types of graphs that will be given to you. And do not worry if you see them. Suppose this is force and N. This is like X, M. And then another graph like this they've given, where this is force and X. This is the same extension in meters, force in newtons, sorry, extension meters. So the first graph basically shows you a straight line like this, and then it curves a bit towards X, and they show, okay, this is the loading, and after the curve it just comes back. So they say, okay, this line comes back, and that's the unloading. Okay, so then what happens is, in the next set, this you see another curve like this, which says there's a straight line like this, and now it's going curved like this, and they show you that this is the loading. And then the line doesn't really come back from the same point. In fact, the line basically goes like this. So when it comes back through unloading, it has a permanent extension left right here. Okay, now between these two graphs, the main difference is that in this one, elastic limit is not crossed, and if because the elastic limit is not crossed, so it returns back to original shape after unloading. Because if you see, it does not basically has any extension shown permanently after that, so that's important. But in this one, elastic limit is crossed, which basically means it does not return to original shape, hence it is deformed permanently. So as you can see, even when the force is 0, it still is showing some deformation. So it means that now you can't fix it, unfortunately. Okay. Ahmad, do you understand? Aman? Everything is clear? Hmm. Okay, so I'm gonna send you this copy of notes to you, and then I'll send you the worksheet for it that I'm gonna probably check tomorrow. So, yes, yes, yes. Okay. So this is deformation notes, and now I'm gonna put the assignment here. Let me just go to okay. Deformation. Okay, that's cool. Open in. It's oh no. That's not fair. So that would be deformation MCQs. So I want you people to basically do this today, and tomorrow we'll start checking it. Okay? And I hope to see you tomorrow then. And you may start now. Please don't leave the class. You can continue.